At this point, it's my privilege to introduce our plenary speaker today, who is Bruce Buffett from the University of California at Berkeley. Bruce is has a well-known fluid dynamicist, I would say, expert in geophysical fluid dynamics, whose expertise and research contributions span an incredibly wide range. Much of what he's known to for this community is his work on coarse circulation, evolution of the magnetic field of the planet, and particularly its timing, and possible structure in the outermost core, which is a very provocative topic for this community. But he's also had very broad contributions in other domains as well, including an extended set of work on clathrates. So one could loosely describe him, I suppose, as working on everything from clathrates to the core, and that's not alphabetical, that's hopefully spatial. Bruce got his PhD from Harvard, working on, I believe, nutations of the Earth, modeling nutations of the Earth, then did a postdoc at the University of Cambridge, and I think it was in applied math, if I remember right. He then moved on to a faculty position at the University of British Columbia, then moved to Chicago, and then finally landed on the Golden Coast of California at the University of California at Berkeley. And today he'll be talking about impediments to progress in our understanding in the dynamics and evolution of planetary interiors. So we're going to hear a talk on impediments, and I'll turn it over to Bruce now. Thanks so much for joining us today, Bruce.
Thanks for the opportunity to participate, and I'm really quite pleased to be able to sort of contribute to the discussions that you're having about the future of compress. You may notice that I've changed my title a little bit from what I originally gave the organizers, but the goal is the same. My plan is to introduce the relevant priority science questions for this community that were raised in the National Academy report. Talk a little bit about some of the recent progress on these questions, and really use that to set the scene for the research opportunities for the high pressure community moving forward in this area. So let's get started and jump into the research questions. So the first research question in the report really could be paraphrased as, how does the motion of a conducting fluid generate the planetary magnetic field? And we know that the influence of rotation has a strong effect on the form of convection we expect in the core. And we know that this style of fluid motion is actually very effective at generating magnetic field. But it's also true that the magnetic field exerts a strong feedback on the fluid motions. And as a consequence, the field that we see in any particular planet is going to be an emergent property of the interactions, nonlinear interactions between these two things. Now, the physics of this problem is pretty well understood. I mean, there's no real serious debate about this. So the challenge in addressing this question is largely one of computational issues, and secondly, understanding the appropriate physical parameters to put into these particular models. The second question in the report could also be paraphrased as follows: can we predict the style of tectonics on a terrestrial planet? And this is a more challenging problem in the sense that the physics really still is not completely well understood. The form of the rheological models that we need to use to produce these features is not well understood. Numerical models that have attempted to do this often use very ad hoc assumptions. And so I think we're really a long way away from predictive understanding of this behavior. There's a third question that I could add that's actually not in the report, but would connect the first two, and that is there a connection between the magnetic fields of a planet and the tectonic style? And I think the answer to this question is almost certainly yes. The energy supply, or the power that generates the magnetic field, ultimately is controlled by the amount of heat flow that's leaving the core across the core mantle boundary. And the magnitude of that flow is largely determined by mantle convection, and that can be significantly influenced by plate tectonics. So in that sense, the magnetic field is a very sensitive diagnostic of the internal dynamics. So let's start with some recent progress, and certainly in the context of the origin of the magnetic fields, there's been a lot of progress in terms of computational capabilities. What I'm showing you here are two slices of the radial flows from numerical dynamo models. We're looking at the radial flow, and in this sort of image on the left-hand side, I would call this sort of a typical model. These radial motions you could almost think of as being plumes. You see red things rising up and blue things sinking down from the core mantle boundary. And this calculation is done at an Ekman number of 10 to the minus 5, which is the number we use in these calculations to characterize the value of viscosity that we're using. As I say, this would be a fairly generic or typical model for today. This other model is run with a viscosity which is 500 times smaller. And you can see some staggering differences in the structure of the flow. The length scale of the flow is much, much smaller. These flows are much, much more turbulent. And another interesting feature of these flows is that the role of waves is a very dominant component. Waves of every sort of description are present in this particular simulation on the right, and those waves and accelerations are largely absent from sort of the more typical model. So this is giving insights into sort of perhaps a clearer picture of what the core dynamics actually looks like. So there have been some attempts to try to characterize the waves. In this particular recent study of Aubert and Gillet looked at the fluid accelerations near the top of the core from one of their recent numerical models. And a couple of things you'll notice. In the top image is sort of the full resolution of the calculation. You can see that the accelerations are pretty small scale. And also these accelerations are pretty large. These numbers won't mean anything to you, but take my word, these are pretty large. What they've done in the panel below is to filter this to the larger scales, because it's the larger scale flow that will sweep around magnetic field and allow us to detect these motions at the surface. And what we see is that the accelerations are now quite a bit smaller. So most of the accelerations are in the small scale flows, but we still see a lot of motions, a lot of accelerations, mainly in the equatorial regions, to somewhat extent in the polar regions. And again, this is almost entirely due to waves, and these waves are entirely absent from the standard model. So there's actually some support for the existence of these waves in the magnetic field. And in particular, what I'm showing you here are observations, really strictly speaking, maybe models based on observations of the second time derivative in the radial magnetic field. This is particularly important because the second time derivative of the magnetic field depends mainly on the fluid acceleration. So it's a window for us to look down to the core and try to sort of infer some of these fluid accelerations. And in fact, these observations are really only possible with magnetic satellite observations. So you can see that there are regions of acceleration in the equatorial regions. There are regions in high latitudes. And very recently, we've tried to analyze these changes using techniques that are designed to extract traveling waves if they're present inside these observations. It's called complex EOFs. The details are completely unimportant. But just to show one example, looking at this box region here in Southeast Asia, this is a plot of longitude versus time, just one slice through this model. And this is the first mode that we've recovered from this data analysis tool. And I think that you would agree that you can sort of see features that are propagating to larger latitudes as time advances. So these are features which appear to be traveling eastward. Maybe the hint of another eastward mode here, perhaps in the second mode. But the point is that the phase velocities of these disturbances are on the order of hundreds of kilometers per year. And so that's on the order of 10, perhaps more than 10 times the fluid velocities. So these are almost certainly going to be waves. We also see similar sort of thing in the northern hemisphere. We see sort of evidence of westward motion. These are probably also waves. They're sort of phase velocities in this range, but they're probably a different class of waves. So the important point here is that we have the opportunity to use these waves to probe the dynamics of the core in much the same way that a seismologist would use seismic waves to probe the structure of the internal planet. I think this is going to be an important tool moving forward in terms of our studies of the deep interior. There we go. Okay, great. So let me just sort of try to pitch the following things. I'm going to sort of suggest that these would be useful things to sort of focus some energies on, and I'm going to try to provide rationale and explanation for these specific choices. But of course, better equations of state are always going to be useful for the purposes of comparing with seismic observations. But I think from the point of view of the dynamics, the transport properties of core materials is going to be absolutely essential. I think the issue of phase equilibrium between silicates, oxides, and iron alloys, particularly at the core mantle boundary, where all three of these things are in contact, is also going to be an important component, as we'll see moving forward. The role of volatiles, I think, will also be important, in particular the way in which the volatiles can potentially change the phase equilibrium of these compounds. And then finally, the rheology of the mantle is really a long-standing goal to really understand the origin of plate tectonics. And I've written this in slightly lighter font because I'm hoping that Shun will actually pick this up during his talk, so I won't really focus on that. Certainly in the last 8 years or so, one of the really striking things to me that has come from the high pressure community is this notion that the thermal and electrical conductivity of iron alloys is much higher than we used to think. This is just one particular study from Monica Pozzo and colleagues showing the electrical conductivity along an adiabat through the core for two different iron alloys in this particular calculation. And similarly for the thermal conductivity increases as we go into the interior, both as temperature and pressure are increasing. And the fact is that these are on the order of a factor of 2, maybe a little bit larger than the values that we were using 10 years ago. And this has profound implications for the dynamics of the planet. In particular, it affects the core heat budget. So we know that a large fraction of the core must be convecting because it must be producing the magnetic field that we see. So in those regions where the fluid is convecting, we know that it will be well mixed. We expect the temperature to be very close to an adiabat, within probably millikelvin of an adiabat. And as a consequence, the conduction that we have down this adiabatic gradient becomes larger and larger and larger as we start to increase this thermal conductivity. And even a factor of 2 in the thermal conductivity can make an enormous difference. With these much higher values that have been suggested in the past few years, it's now not really clear how the magnitude of the heat flux that we can conduct down the adiabat compares with the amount of heat that the mantle is actually taking from the core. It's possible that the CMB heat flow is greater than this, but it's also possible that the CMB heat flow is less than this. And there are important consequences as a result. So just imagine we're in the case where the CMB heat flow is a little bit bigger than the adiabat. Then we have essentially 3 sources of buoyancy that are stirring fluid motions and powering the magnetic field. We've got cold fluid, which is sinking from the core mantle boundary. The core is cooling. We're growing the inner core by solidification, segregating light elements into the fluid and releasing latent heat. And as I say, all 3 of these buoyancy sources will be driving convection. If we sort of zoom in on the core mantle boundary, we see that we've got, if the adiabatic value is a little bit less than the value that the mantle is taking away, this region will be constantly being cooled and provide a continual source of the cold, dense fluid that contributes to this particular source of buoyancy. But it's equally possible that the CMB heat flow is less than the adiabatic value. And as a consequence, we lose that source of buoyancy in the dynamics of the core. So now we have the situation where the amount of heat that we're delivering by conduction down that adiabat exceeds the value that the mantle is taking out, and we end up accumulating warm fluid at the top. There are, I guess, 2 potential options for what would happen. It's certainly possible that chemical buoyancy, the light elements, could essentially stir this warm fluid back into the interior. That would divert energy from the magnetic field, but at least in principle, it's possible energetically, but it's probably unlikely dynamically. And so the more likely outcome of this would be to develop a thermally stratified layer at the top of the core. Now, there is some evidence for stratification. That's a long-standing argument that sort of still, I think, is not completely resolved. The seismic observations come primarily from these multiply underside reflectant P waves that travel first as S waves through the mantle. And by analyzing the arrival times of these multiply reflected waves, the inference has been that the rough top 300 kilometers or so of the mantle is slow relative to ground. There, I would say maybe a couple of limitations of the seismic observations, at least for this particular context, is that you're measuring P wave velocities rather than density, and you're measuring deviations from another seismic model rather than from a well-defined adiabatic state. And so the interpretation and the observations aren't completely and directly relevant to the question that you'd really like to know. So the other way that we can go after this is try to detect some of these waves that I mentioned earlier. And there's been suggestions, partly by me certainly, that we do see evidence for these so-called MAC waves in variations in the magnetic fields at the surface. And the attraction here, I think, is that these only exist in the presence of stable stratification. So if there was no stable stratification, we would not expect to see these waves. And once we've detected them and characterized their propagation properties and other sorts of things, we get a direct constraint on the density stratification, which is usually expressed in terms of a so-called buoyancy frequency, which depends essentially on the gradient and density through that layer. Now, on the basis of these observations, we've concluded that the value of the buoyancy frequency is roughly comparable to the rotation frequency, essentially. So not strong stratification, but certainly dynamically important. And that the thickness is on the order of about 140 kilometers. And you can get both of these features with thermal stratification if you argue that the CMB heat flux is about 84% of the adiabatic value. So if you take some of those higher thermal conductivities and suggest that the adiabatic heat flux is on the order of 16 terawatts, this analysis would suggest that the heat flux coming across the core mantle boundary is about 13 terawatts. Okay. I just mentioned briefly evidence for other waves because I mentioned earlier that we do see evidence for waves in the second derivative of the radial field. And in particular, these high latitude waves, these pulses essentially are drifting to the west, can be explained, and their propagation properties can be explained by a layer of thermal stratification, which is comparable to what we need for the MAC waves. So going forward, I can see a situation where we have a variety of waves that we can use to provide supporting evidence for the structure in the Earth in much the same way that you would expect seismologists using body waves in normal modes to be able to recover the same information about the Earth by effectively independent methods and observations. Okay, so the consequences of stratification are pretty important. It's not so important for the present day Earth, I would say, because the sources of buoyancy associated with inner core growth, compositional effects, and latent heat effects are enough to drive the dynamo today without concern. But as we go back in time to a point where the inner core is not present, then essentially the cold thermal boundary layers, the cold downwellings, is the only source of buoyancy that's driving the flow. And so if we're in a situation prior to the inner core and the CMB heat flux is less than the adiabatic value, then the dynamo is possible. We'll have this buoyancy force. You don't need very much to make this work, and likely everything is fine. But if the CMB heat flux is still below the adiabat at the time when the inner core prior to the formation of the inner core, then we have a problem. Thermal convection will likely fail, and we might also expect the dynamo to fail unless there's some additional source of buoyancy that we can use to drive these motions. And so this has motivated a fairly recent discussion of the possibility of chemical interactions with the mantle. The idea is when the core forms, it acquires a certain amount of light elements, oxygen, silicon, magnesium, whatever your favorite is. And that the idea is that the solubility of these components decreases as the planet gradually cools. And so these light elements are going to exsolve from the core, potentially underplate the mantle. Removing these light elements will leave behind a fluid which is a little bit more iron rich, and that potentially provides sufficient buoyancy to drive convection in the core. The effectiveness of this source of buoyancy depends a lot on how much of the element in question you've actually got in the core. And it also depends on the temperature dependence of the solubility of these various elements. The point is that if you knew these things in principle, it's fairly easy to construct physical models to test the viability of these ideas. And I wanted to just simply show you one example to illustrate the challenges and potentially the problems. So this is a model, some work that I did with Jimmy Badrow a couple of years ago for an AGU meeting. In terms of background, we're assuming a bulk mantle, which is roughly pyrolytic. And we're assuming a bulk core composition too, basically, one that has a little bit more silicon and one that has a little bit more oxygen. And so the idea here is that we're allowing the core to gradually cool. We're using Jimmy's thermodynamic models to predict the solubility, and we're just predicting which way the light elements are flowing across the core mantle boundary. And this particular setup chooses positive values to be from the mantle into the core, and then the negative values are then the exsolution case where the light elements are coming from the core and they're moving into the mantle. And so what you can see from this simple model is the fact that over most of geological time, going from present to 4.5, from zero origins of the Earth to 4.5 billion years, we're mostly having oxygen and silica go into the core in roughly the proportion of 2 to 1. And so this is basically suggesting that silica is moving from the mantle and being added to the core over geological time. And it's really only in the last few hundred million years that perhaps that process has reversed and we get the exsolution process. And so this is not going to be very effective in generating an early magnetic field. On the other hand, there are studies that suggest that in fact, silica exsolution could power a magnetic field from the earliest days. And the fact that these two results are in completely opposite conclusions, or completely opposite outcomes, is really, or can be completely attributed to the thermodynamic models that we've used in these calculations. So in order for us to really make sense of the chemical interactions and to see whether or not this is actually a viable source for powering an early magnetic field, there's clearly going to have to be a lot more work done to make sure that these thermodynamic models for solubility are more robust and more reliable. So there's going to be a lot of work that has to be done there to resolve this question. Okay, so there's a number of very interesting things that can take place once you start to entertain the idea of chemical interactions with the mantle. And in particular, this is just one example, small lateral variations in the FeO content at the base of the mantle, maybe on the order of percent level, will cause local variations in the amount of dissolved silicon oxygen. So you have a certain amount of FeO content here. There will be a local equilibrium that gets established at the core mantle boundary at this particular location. If at some other part of the core mantle boundary, you have a slightly different amount of FeO content, you'll have slightly different concentrations of SiO and oxygen in equilibrium with the fluid at that particular point. And these are quite small variations, but they actually produce fairly substantial variations in density. So using, again, Jimmy's thermodynamic models, the lateral density variations that we would expect just from these very small variations in FeO content can be on the order of a part in 10 to the 4. Whereas the typical convective fluctuations that we see in the core might be on the order of 10 to the -6. So these chemical interactions are potentially going to be driving a significant fraction of the flow that we see at the top of the core. And it's something that we've really never thought about before. Another interesting, maybe more provocative idea is the idea of extending what we mean by a deep water and carbon cycle. In the model that I showed you earlier, over most of geological time, we have mantle minerals transferring silica and oxygen to the core. But you can imagine if subducted materials with water, carbon, and other things arrive at the core mantle boundary, it's very likely, based on the affinity of these compounds to iron, that you would transfer the carbon and the hydrogen into the core. And in a similar way, you'll produce a slightly more buoyant fluid here, even with small fractions of increases in carbon and hydrogen to the core. You'll produce variations in density that will drive flow. And in fact, those flows will travel across the surface of the core mantle boundary. And if they encounter regions where the concentrations of hydrogen and carbon are a little bit lower, it's certainly very plausible that you could start transferring some of those elements back to the mantle. And so it's possible that a deep water and carbon cycle on the planet ought to be including at least the upper part of the core as well. Okay, well, let me bring this to a close by looking at some of the wish list things that I would love to see this community work on. The issue of thermal and electrical conductivities of iron alloys is absolutely essential, both in the liquid and the solid phases. And I would stress that both properties are distinctly important. The values of thermal conductivity are important for the thermal budget and the buoyancy that drives these convective motions, but the electrical conductivity in its own right is important for determining the properties of the waves, and in particular, determining the damping of these waves. And so this is actually quite a critical piece of information, and we really need both. The viscosity of liquid and solid alloys is important in the context of inner core anisotropy. Really understanding how the inner core deforms and on what sort of timescales is really important to addressing that problem. But even the liquid viscosity is actually important, maybe surprisingly so. And in particular, the presence of turbulence due to precessionally driven flows in the core depends quite sensitively on the liquid viscosity. And the current Earth, the current precessional state of the Earth with sort of nominal values of viscosity, puts the onset of turbulence in the Earth sort of right at the knife edge. It might be turbulent and it might not. And so knowing a little bit better what the fluid viscosity is might allow us to sort of assess whether or not turbulence or not is an important component of the precessional flows. I've mentioned the issue of the phase equilibrium at the core mantle boundary. This is really essential for understanding the nature of the chemical interactions between the core and the mantle. And there's clearly a lot of disagreement among current results, and we need better strategies for figuring out how to do this work more consistently so that we actually agree on what to expect. And then finally, and maybe as a personal note, I would love to see a lot more work done on the elasticity and deformation of solid iron, really as a way of coming at the question of the anisotropy in the inner core. This is a problem that has been kicking around for a long time, and I'm not sure that we've made much progress on it. And part of the difficulty, I think, is that some aspects of the material properties at high pressure and temperature are still quite uncertain. And so I sort of tend to stand behind the HP community, high pressure community, and say, well, you have to get this sorted out before we can make any progress. If you were able to do this, then I would no longer have any excuses to not figuring out how this actually develops in the core. And with that, I say thank you, and I would welcome to answer any questions.
Thank you, Bruce, for a very provocative talk. That's why we brought you here, for a provocative talk. And I think we have one question right now in the chat, and I am scanning for other hand raised. Kat Armstrong, do you want to ask your question and unmute and ask your question, or should I just read it? So in terms of your compositional variations near the top of the outer core, what is the length scale over which these kinds of small compositional variations would matter?
Okay, so we're thinking about in the mantle, or are we thinking about in the core, I guess?
I think it references for when it showed up the compositional variations at the very top of the outer core, where you had delta rho on rho of 10 to the minus 4.
Yeah, right. So, yeah, right. So fair enough. So the point is that we're imagining these are pretty large scale features. And so, you know, it's maybe remarkable to recognize the fact that the fluid motions that we see in the core, and these are on the orders of tens of kilometers per year, can be driven by temperature anomalies, which are sort of millikelvin. And that's just by virtue of the really low viscosity. So, you know, if you have compositional variations over very, very short distances, you'll produce very, very strong flows. And the remarkable thing is, even those tiny compositional variations over planetary scales will still drive significant flows. So the fact is, both will matter. The very small scale flow would be hard to see and detect at the surface, but it could be potentially important for a variety of things going on in the planet.
Let me follow up real quickly before going to Alex Gontra. how dependent is that on the topography at the core mantle boundary? Are you entirely
Yeah,
dependent on
so
flow?
that's a great question. That's a great question, and it would matter a lot. In fact, these solubility relations are mostly dependent on temperature, and so you could imagine in topographic features, if you live in the core like I do, then places where you imagine the core mantle boundary moving down. Maybe, in fact, let's see if I can actually find this here. Chemical weathering, here we go, right. So these features here would be a little bit hotter. And so the solubility of these, local solubility at these points would be a little bit higher than they would be at this point. Not very much, a tiny amount, but it's enough to drive flow. And so you would be having slightly higher solubility here, being swept, precipitating sediments, return flow. You could get something that would be analogous to chemical weathering on the underside of the core mantle boundary by virtue of these chemical reactions. So there's just all sorts of interesting phenomena that could come to play once we understand these things a little bit better.
Great, and I see Alex Goncharov has his hand up. If you could unmute Alex and ask your question, that would be great.
Hi, Bruce. Very nice talk. I would like to quickly comment on the point that you made about increased thermal and electrical conductivity over the last 2 years. I don't think that it's based on experimental point of view. This is what we have now. I think now we have a kind of debate still, and I wonder if that debate affects anyhow your conclusions.
Yes, okay, well, that's a great point, Alex. I took that slide out in the interest of time. Let's put it back in. So this is a really nice slide that Chris Davies and Sam Greenwood put together, looking at a variety of different experimental results and also theoretical calculations, both for thermal conductivity and electrical conductivity. And when they had electrical conductivity, either experiments or theories, they converted it to a thermal conductivity using the Wiedemann-Franz law. They used the slightly non-standard or non-ideal Lorentz number, and they also tried to extrapolate things to the core mantle boundary conditions. And so this is the summary of the results. And so you see a wide range of results. You see some values, not a lot of values here, sort of in the 80 to 100, which is significant, but you're absolutely right. You see other studies where these values are much lower. Values on the order of 40 or so were the values that we're using before. A lot of these problems with thermal conductivity would go away if these were actually the correct values. But a factor of 2 is enough to make a difference. And so we really need to know. And so the fact is, if we were doing science by democracy, we would say, well, the majority wins and that's how we move on, right? But what we would really like to know is what's the truth. And so if these values are correct, you're absolutely right. A lot of the problems that I described would in fact go away.
Well, there was a more recent work in 2021, which I think it's not cited here.
No,
it's
it isn't.
Work of a firm of Wien and John Cohen group.
Right.
In parallel, so you may want to add that.
Right. Okay. But the point is that there's still a lot of disagreement, I think. And so because it is so important in terms of the way in which we think the system operates, that we really have to nail that down. I mean, it's a hard experiment, a difficult property to determine, and factors of 2 make a difference. But it's important, and we have to figure out a way to sort of solve this controversy.
Thank you.
Okay, I see Yanbin Wang has his hand up, and I think we have time for at least one more question on this, maybe 2 actually, since I see another hand up. Okay, so let's go to Yanbin. If you could unmute, go ahead.
Okay, thanks. Thanks, Bruce, for a really interesting talk. Correct me if I'm wrong, I get an impression that the process of all these parameters seems to be that, I mean, the whole process is very sensitive to very small variations in a lot of processes.
Right.
Could you comment on the stability of the system? So
Yeah.
for long-term stability, how are these things fit in the long-term picture?
Yeah. Okay. So I would say if we were to go back to the old values of thermal conductivity, where there was really no question that the mantle could draw the amount of heat out of the core that was required to power a dynamo prior to the presence of an inner core, then I would say that's a perfectly stable process. Mm-hmm. If our results of thermal stratification are correct and the CMB heat flow is a little bit less than the adiabatic value, then we either need the CMB heat flux to be a little bit higher, say 500 million years ago or 1 billion years ago, whatever the appropriate number is. And so the stability comes in that, and it's not really being sure of where our energy sources are.
Okay.
I mean, the fact of the matter is we know that there's been a field for at least 3.5 billion years and probably longer. So we know that the energy has been provided, and the problem is really on us to figure out where that energy is coming from. And so I think the key issue in terms of deciding where to focus our energies are really going to be determined by where the transport properties, what their most reliable values end up turning out to be.
Okay, thank you.
Great. I think we have time for one more question, and let's
Exactly.
go.
About the viscosity of the solid iron, how accurately are you hoping? Or how accurate would be a useful measure?
I think order of magnitude would be great.
Okay.
It affects a variety of things. It affects the level of stress that you can have, which is important for the mechanisms that would actually drive the process to align grains. And so, if it's really very low viscosity, sort of like ice, for example, it's really hard to imagine how this works. I mean, the connected with this, though, is the fact that if the thermal conductivities really are very high, and they seem to get higher at higher pressures, then it's very likely that the inner core would be thermally stratified. And so any mechanism that relies on radial flow is not an option, right? And so viscosity for me, a useful number would be probably order of magnitude.
Okay, thanks.
Great. That's almost perfect timing. That was a great talk, Bruce. We'd like to thank you for spending your early morning with a group of high pressure folks. That's service above and beyond the call of duty.
Yeah, no, my pleasure. This is a very important community, and so I'm really cheering you guys on. I hope for the best.
Well, thank you so much for your talk, and thanks for contributing to this.
Yeah.
Yeah.
See you guys.